Section 8, the octet rule and bonding. Chem Talk, forming compounds, the octet rule. In the Investigate, you explained the formation of several compounds by determining how many electrons are transferred or shared between atoms. Scientists explain these observations using the octet rule. This rule states that atoms or ions tend to be more stable with an outer shell configuration of 8 electrons, as is naturally the case with stable noble gases. A filled outer shell of electrons is a driving force for chemical reaction to occur. Therefore, atoms will gain, lose, or share electrons to obtain 8 electrons in the outer shell. The octet rule works well with almost all of the elements found in the first 3 rows of the periodic table. However, there are 2 exceptions to this rule. The elements in the first row of the periodic table have only 2 electrons, so only 2 electrons are needed to fill the 1's shell. The other exception is found in the transition metals. Ionic and covalent bonds. Ionic bonds are formed between 2 atoms when the valence electrons of one atom are completely transferred to a second atom. Typically, 1, 2, or 3 electrons are transferred and 2 ions are formed, a positive ion and a negative ion. The electrostatic force of attraction between the 2 charges, ions, is the ionic bond. Valence electrons and bonding can be illustrated using electron dot diagrams, sometimes called Lewis structures. In these diagrams, each valence electron is indicated by a dot adjacent to the chemical symbol for the element. The table below shows the electron dot structures for the first 20 elements. Notice that the electrons shown are only the valence electrons, not all the electrons of the element. Also notice the electron dot structures are identical for groups of elements in columns. This is why lithium, sodium, and potassium have similar characteristics, as do fluorine and chlorine. Examples of ionic reactions and bonds from your investigation are or sodium chloride, or calcium chloride, or aluminum chloride. By giving up electrons, the metals sodium and aluminum take on the outer electron shell configuration of the noble gas neon, which has 8 electrons. Calcium metal becomes a calcium ion with the configuration of argon, which also has 8 electrons. By taking on an electron, each chlorine atom becomes a chloride ion with the electronic configuration of argon. You may have noticed that the column headed by carbon in the periodic table has not received a lot of attention so far. In an earlier section, you learned that atoms of carbon contain 4 valence electrons. To form an ionic compound, carbon would have to lose 4 electrons and take on a very high charge of positive 4, or gain 4 electrons to take on the equally high charge of negative 4. Either way, carbon would have a very high electrical charge of 4. Because such a high charge is unstable, carbon does not typically form ionic compounds. Instead of giving or taking 4 electrons, carbon atoms share 4 electrons to fulfill the octet rule. The result is the formation of covalent bonds in molecules. While carbon has the ability to form large, complex molecules by bonding with itself, all elements with 4 or more valence electrons can form covalent bonds. By sharing electrons, these atoms are associated with 8 valence electrons, thereby following the octet rule. Water is a covalent molecule composed of 2 hydrogen atoms and 1 oxygen atom. H2O. Hydrogen has 1 valence electron and needs 1 more to have the electronic structure of helium, a noble gas. Oxygen has 6 valence electrons and needs 2 more to have the electronic structure of the nearest noble gas, neon. Using electron dot diagrams, water can be shown to bond as follows. Or H2O, water. You can count 8 electrons around the oxygen atom in water. You can also see that after the reaction, each hydrogen atom has its required 2 electrons. Whenever possible, electrons are shown in pairs, and each covalent bond consists of 2 electrons. The pair of electrons forming the covalent bond between hydrogen and oxygen are called bonding electrons. Usually, for ease in writing structures, scientists replace a bonding pair with a single line. The 4 electrons on the oxygen atom in water that are not used for bonding are called non-bonding electron pairs or lone pairs. Non-bonding electrons may be shown in an electron diagram of a molecule. For simplicity, the non-bonding electrons may be omitted with the understanding that they are part of an octet. An example of each type of diagram for water is shown below. Or naming compounds. You may have noted that the names of the ionic compounds you have studied have all started with the name of the metal. This is followed by the nonmetal part. All of these compounds are binary compounds, that is, made of 2 elements. The names of binary compounds always end with the suffix "ide". There are exceptions, such as compounds with common names like water and ammonia. The International Union of Pure and Applied Chemists, IUPAC, is the world authority on naming chemicals, and it has detailed rules for naming every chemical ever discovered or made. However, only a few basic rules are needed here. Number 1. For binary compounds, the element with the most metallic characters placed first, and the name usually ends in "ium". Number 2. The nonmetal part of the binary compound is placed last, and the name usually ends in "ide". Ionic names for nonmetal families are as follows. The nitrogen family: nitride, phosphide, arsenide. The oxygen family: oxide, sulfide, selenide. The halogen family: fluoride, chloride, bromide, iodide.